After that result, next is a sequence Xn of vectors of Hilbert space H is weakly convergent. If this sequence is weakly convergent, then it satisfies two property, property number A and B. If and only if property number A, this sequence is bounded set. Number two, property number B, the inner product of xn comma y is convergent for every y belongs to M, where M is dense in H. So M is a dense in H. Now let xn sequence, which is a weakly convergent in H. Then by definition, this is a definition that is in equation number 1. If we take gny, which is equal to y comma xn, then this is an inner product, and Rice representation theorem, the first part of the Rice representation theorem, the inner product is a bounded linear functional with the norm of Gn, the norm of this vector is equal to norm of Xn. So it implies Gn belongs to H star with the norm of Gn, which is equal to norm of Xn. Now since Gny is convergent, so that is by using equation number 1. This part is X, this part is Gny, so this is a convergent to this number. So since Gny is convergent, every convergent sequence is a bounded, so Gny is a bounded. It implies Gny is a bounded. By uniform bounded principle, again norm of Gn is a bounded for every n, and norm of Gn is equal to norm of Xn. So norm of Xn is a bounded set, which prove the part number A. Now to prove the second part, using equation number 1, we know that this is a convergent for every y belongs to H. Now what is M? M is a dense in H. If M is dense in H, then closure of M is equal to H. It means M is a part of H. If any condition is true for H, then that condition is also true for every subset of H. So since M is part of H, so this condition is true for every set which is a part of H. So this condition is true for M, which prove the result number B. Now converse part. Now here A and B are given, and we want to prove that Xn is a weakly convergent to X. Now by A part, every bounded sequence has convergent subsequence. We know that. Now by A part, the given is the sequence Xn is convergent. Now we know that every bounded sequence has convergent subsequence. Then Xn sequence has convergent subsequence Xnk. So we consider Xnk is a convergent subsequence of sequence Xn. And by B part, limit n approaches infinity yxn, which is equal to inner product yx for every y belongs to M, where M is dense in H, it means closure of M is equal to H. Now we take some y belongs to H. H is equal to M closure. Then y belongs to M closure. If y belongs to M closure, then by definition of closure, there exists a sequence Zn in M such that Zn approaches to y as n approaches to infinity. Now from equation number 3, we get, what is equation number 3? So this is equation number 3. What we get? We get for every y belongs to M, this condition is satisfied. Now what is Zn sequence? Zn sequence in term of M. belongs to M. So this condition is satisfied for every vector belongs to M. It means this condition is satisfied for every vector Zm because Z1 belongs to M, Z2 belongs to M, Z3 belongs to M, Zm belongs to M. So it means equation number 3 is satisfied for vector Z1, for vector Z2, for vector Z3, and so on up to for vector Zn. So it means this from equation number 3, we get this condition is satisfied for Z1, Z2, and so on for Zn. In general, we know that it is for every M. M is running from 1 to like 1 to infinity. So that is in equation number 5. Now by double limit theorem, we know that in the limit m approaches to infinity, limit n approaches to infinity of this value is equal to. Similarly, here we can replace limit n approaches infinity. Here limit m approaches to infinity, they are equal. Now first we find the value of this limit. Now from this, by using limit n approaches to infinity, so this value is equal to limit m approaches infinity, inner product zm comma x. So this is by equation number 5. So by using this result. So it implies this value is zm comma x. Now again since inner product is continuous. If inner product is continuous, so this limit can be taken inside. So inner product of limit m approaches infinity, zm comma x, this value is equal to y. So this is y comma x. So this is by equation number 6. So this is one part of the double limit. Second part, now first we take limit m approaches infinity. Now this value is equal to this, and this value is equal to limit n approaches infinity y comma x. So this is a equation number 7. Now equation number 6 and 7 are equal. If equation number 6 and 7 are equal, then limit n approaches infinity y comma xn, which is equal to inner product of y comma xn. So it means the sequence xn is weakly convergent to x, that prove the result of this